Welcome to the deep dive.
Hey there.
Today, we're plunging into some really interesting physics, an experiment that's sort of questioning a fundamental concept.
Yeah, symmetry. And the source we're looking at, unpacking for you, it's research from Mississippi State University and Jefferson Lab.
Thomas Jefferson National Accelerator Facility, right? It just came out in Physics Letters B.
That's the one, led by Professor Dipankar Dutta. Pretty significant stuff.
Okay, so our mission really is to help you get what this experiment found. It's about quarks, these tiny, tiny particles.
Building blocks.
Exactly. And why these findings might actually, change how we think about matter itself, like discovering a little unexpected detail in a rule we thought was solid.
Well put. Because, symmetry has been just huge in physics for ages.
Right.
It's this powerful idea, basically suggests things behave the same or look the same, even after you do something like rotate them or reflect them, mirror image stuff.
And it underpins so much, right? From crystals to, fundamental forces.
Everything. And it's especially key when you get down to the really small scales.
The particles inside protons and neutrons?
Exactly those, protons, neutrons. They make up the core of, every atom you interact with. And they themselves are made of quarks.
So this experiment at Jefferson Lab, what did they actually do?
They essentially smacked these quarks with high-energy electrons, very precisely.
Okay. And this is where it gets interesting for you listening. According to this research, what they saw, it wasn't quite what they expected based on perfect symmetry.
Right. When the quarks got hit, they didn't always react in that perfectly symmetrical way theory predicted. And this is really important. Professor Datta's team notes that the assumptions about these symmetries hadn't really been tested quantitatively.
Yeah.
Not like this, not at this extreme precision.
Oh, hang on. The results are saying there are these subtle cases where the symmetry just isn't perfect.
That seems to be it. Their data indicates these little breaks in symmetry, which means we need to sort of tweak our models.
So the basic rules we thought governed quarks, the fundamental bits of matter, they're not perfectly symmetrical if you look really closely.
That's the key takeaway for you from this experiment, yeah. It does challenge some existing ideas in nuclear physics.
And gives us better insight into the strong force, the glue holding things together.
Exactly. New, more precise insights into that incredibly powerful force that binds quarks and ultimately holds atoms together.
What's cool is that finding these tiny deviations, it's not just about finding flaws, it's actually making the tools better, right?
Absolutely. It refines the theoretical toolkit physicists use. We get a more accurate picture of the subatomic world.
So it makes our understanding sharper.
It really does. And it changes how we might need to, interpret future experiments, looking at quarks, looking at the structure of matter.
Makes you wonder what else is slightly off from what we expect.
It encourages us to probe deeper, definitely.
Yeah.
Look for other subtle asymmetries that might be hiding in plain sight, almost.
Okay, so wrapping this up for you. This high-precision experiment showed quarks, the bits, inside protons, and neutrons don't always rigidly follow the symmetry rules we assumed, not under these specific test conditions.
It's a refinement, a correction maybe to our basic understanding, a more nuanced picture.
And the research points out, this kind of basic science pushing the edge, it's not just for textbooks.
No, absolutely not. It can open doors down the line, things you might see eventually in energy tech or new materials, maybe even medicine. You never know where fundamental insights lead.
It sharpens our view of the universe's most basic forces and, challenges those long-held assumptions.
It really makes you think, though, doesn't it? If something seemingly as fundamental as symmetry, right down to the tiniest scale, can still surprise us when we get better tools to look.
Yeah.
What other core assumptions, across all of science might be ready for a fresh look, a bit of a re-examination?